All right, let's get started. So last class we were talking about substitution reactions of alkyl halides. All right, so just to look at a simple substitution reaction, we're going to take our alkyl halide and we're going to be substituting that halogen with some nucleophile. All right, so we're replacing our halogen with our nucleophile. And then we talked about the stereochemistry of these reactions. We said if we had a primary alkyl halide, there's nothing to worry about. There's no sort of stereochemistry. But if we have a secondary alkyl halide, we're going to see an inversion in that stereochemistry, which means that if my reactant has that halogen on a wedged bond, for example, that's going to be converted to a dashed bond, or vice versa, right? So this inversion, this stereochemistry inversion, means our dashes go to wedges or vice versa, okay? And we said that that's because when the nucleophile attacks, it has to attack from the opposite side of where that leaving group is, right? The leaving group is in the way. It can't go this direction. The leaving group's in the way, right? So it has to attack from that opposite side. Cool. All right, let's just practice this real quick then. One of the things where these nucleophiles, they can be kind of simple and tiny, or they can have some carbons on them, which means that our product gets a little bigger and uglier. All right, and we need to be able to follow those here. So everybody just take a second and give me the product of this reaction. All right, so we had some fancy terminology even. We called this thing with a lot of electrons our nucleophile. All right, and in particular, that nucleophilic site is that oxygen that has all that electron density. And it's going to react with our electrophile, which is our electrophilic site on this molecule is that carbon that is bonded to that halogen, right? That halogen's stealing all that electron density because it's so electronegative. And so these are the two atoms that are going to have this new bond formed. So I'm going to draw my hexagon. Here's that blue carbon that used to have the halogen attached. Now it's going to have that oxygen. And since this oxygen had this carbon attached, I'm going to make sure to draw that in as well. Okay? Now that my oxygen has two bonds, it has two lone pairs. But because this is a secondary carbon, and because we had this dashed bond over here on our product side, I have to be good and I have to show that stereochemistry inversion by putting that new oxygen on a wedged bond. All right, so we have the inversion in our stereochemistry where my dashed bond over here becomes a wedged bond on my product side. All right, we talked about primary alkyl halides and secondary alkyl halides, and we said where we were going to pick up today is with our tertiary alkyl halides. Okay, So let's take a look at a similar molecule, but instead of making it a primary alcohol, or I'm sorry, a secondary alkyl halide, I'm going to put another methyl group on that same carbon to make it a tertiary alkyl halide. All right, and if this halogen is on this wedged bond, I'm sorry, this dashed bond here, that means that the other bond has to be a wedge. All right, now the thing about tertiary alkyl halides that's going to make them different than our other two is that tertiary carbons form stable carbocations. All right, so why is this going to make such a big difference here? Well, up here for our secondary alkyl halides, we said that our nucleophile is going to attack, and it has to go from the opposite side because the leaving group is in the way here, all right? And that's because the nucleophile attacks and the leaving group leaves all in one shot, all in one step here. When we have a tertiary alkyl halide, because they form this nice stable carbocation, what's going to happen is that leaving group is going to leave as the very first step without the nucleophile being involved at all. And this will have the effect of forming one of those carbocations, right? So because tertiary carbons form stable carbocations, we're going to get a stable carbocation. But carbocations are flat. So as soon as this carbocation forms, any dashes or wedges that I had in my reactant, they're gone, right? Everything is now flat about that carbon. Our carbocations are flat. And since they're nice and flat, let's say that I have a nucleophile. I'll take one that we've looked at a few times, these hydroxide ions. There's going to be no preference for which side this nucleophile attacks from. It can attack from this side over here, or it can attack from this side over here. Either one of those is perfectly fine, because now that carbocation has that flat geometry. All right? So what we're going to get here is our same substitution product. We're still going to see that halogen substituted out for that nucleophile, all right? But the difference is now we've gotten rid of all of our wedges and dashes. Now to draw our products, we're going to draw just flat bonds. Okay, so for our tertiary alkyl halides, we don't have any sort of a stereochemistry inversion. We lose our stereochemistry. So our product has those straight line bonds. All right. So let's stack these two examples next to each other here. We're going to start out with our secondary one. We did this one. Secondary carbon, or secondary alkyl halide. Now we're going to do a tertiary alkyl halide. We're going to take that same secondary alkyl halide, but we'll add another carbon on there to make it tertiary. Okay, and then this time I'm going to use that same nucleophile we used in our previous example. I want you all to take a minute and draw me the product of this reaction. Alright, so again, when I do my substitution reaction with a tertiary alkyl halide, it will lose that stereochemistry. So I still have a methyl group here, and I still have my nucleophile attached. I just don't have those dashed and wedged bonds that show any sort of specific stereochemistry. Alright, so for secondary, we said that we were going to invert from a dashed to a wedged bond. For a tertiary, we lose our stereochemistry. We go from having dashes and wedges to no dashes and wedges. Okay? And again, that's because in our mechanism here, in the order in which things happen, that halogen actually just kind of falls off that molecule, creating this flat carbocation. And since it's flat, the enucleophile isn't directed to one specific side. Let's do another example of a tertiary to make a point here. All right, and this time I'm going to use a neutral nucleophile, which remember we said that we're allowed to do with our tertiary alkyl halides. So instead of using hydroxide, I'm going to use water. All right, so we did an example kind of similar to this with our secondary alkyl halides, which had that inversion. But we made a point that if we have two carbons that have this stereochemistry, the only one that's going to get inverted is that carbon that gets attacked, right? It's not like everything flips. It flips for a reason. It flips because that nucleophile is attacking that carbon. So same thing here. We have this stereochemistry. And we said we're going to lose our stereochemistry because this is a tertiary carbon. But importantly, we only lose that stereochemistry about that electrophilic carbon. This down here should still be a wedged bond. Nothing happened. No chemistry happened at that carbon down there. So it doesn't get flipped. It doesn't lose anything. It stays on that wedged bond. All right? The other thing is we had this neutral nucleophile. When I attach a neutral nucleophile like water, what am I going to have to do? I'm going to lose a hydrogen, exactly. So that is going to attach just as OH. Okay, so let's just kind of summarize things real quick. All right, so our summary of our substitution stereochemistry. Okay, for primary alkyl halides. Don't worry about it. There's no issue with your primary alkyl halides. It's not a situation that you're going to encounter with those primary alkyl halides. For our secondary alkyl halides, we have this key word that we want to keep in mind here, which is the inversion of that stereochemistry. All right, but specifically at that electrophilic carbon. And then for our tertiary alkyl halides, we're going to lose our stereochemistry, aka we're going to draw flat bonds. But again, we're going to make a note that that's specifically at that electrophilic carbon. Cool. All right, so today we're going to start in on our second class of reaction with these alkyl halides, what are called elimination reactions. Okay, so let's look at our elimination reactions. We're again starting out with that same functional group, those alkyl halides. Okay, instead of a nucleophile, these reactions are going to use bases. And I know everybody remembers exactly what a base is from general chemistry, but let's just remind ourselves, bases are hydrogen ions or proton acceptors. All right, they take hydrogens away in our reactions. All right, our product of these elimination reactions would be this guy right here. All right, and we've studied these functional groups before. What do we call these products? Alkenes. So an elimination reaction here is going to turn our alkyl halide into an alkene. Right? And you can see how organic chemistry gets very complicated because we learned a bunch of stuff to do with alkenes, right? So we could take this thing and go and do more reactions with it. That's kind of, when you get into organic chemistry, a big portion of that is called synthetic organic chemistry, having a certain starting point and trying to get to an end point by doing a series of reactions. We're going to kind of focus on individual steps here, all right? Now, importantly, I said that there was a base involved in this reaction. There was this proton acceptor here, right? So that means that somewhere, somehow, a hydrogen was lost. Well, where was that? Okay, this is something that's kind of difficult to see because we make our hydrogens implied in our structure. So let's just go in and draw over here all of our explicit hydrogens here. On this N carbon with its one bond, I should have 3 hydrogens that I fill in with my mind's eye. All of these secondary carbons will have 2. And then my carbon on the end, it's got 1 carbon-carbon bond, but also 1 carbon halogen bond. So I need 2 here as well. Okay? So I want you to do the same thing with our product side now. Fill in any missing hydrogens that we have on that product side. All right, this carbon's still got 3, no change. This carbon still has 2, no change. What about this carbon right here? How many hydrogens? Just 1. And what about the one on the very end here? 2. So if I look carefully here, at carbon 3, really I guess if I'm doing my nomenclature it'd be carbon 2 because I'd count the other way, but nonetheless, this carbon right here, notice how in order to get from my reactant side to my product side, it has to lose one of those hydrogens, right? So again, these elimination reactions, they're going to involve bases instead of nucleophiles, and that's because we need to lose one of these hydrogens, all right? We're going to lose this hydrogen. So in our elimination reactions, not only do we lose that leaving group, just like we do in our substitution reactions, we're also going to lose a hydrogen. And importantly, where is that hydrogen located relative to that leaving group? It's not on the same carbon, it's on the next door neighbor, right? So in these elimination reactions, we're going to lose our halogen, our leaving group, and a hydrogen from a neighboring carbon. All right, we'll take a look at what these bases look like next week. We'll start filling in our actual reagents. For right now, we're just going to say elimination reaction, okay? Cool, so I want everybody to take a minute then, based on what we just discussed, I want you to give me the product of the following elimination reaction. You're going to lose a halogen and a hydrogen, but importantly, you should have the same number of carbons on both sides, right? So very easy double check to count carbons. All right, so importantly in this reaction, I'm going to nix this leaving group here. But I'm also going to get rid of that hydrogen on a neighboring carbon, all right? So my product here is going to have that 5-membered ring plus that extra carbon sticking off, but now I'll have a carbon-carbon double bond. Okay, so we have that alkene product from these elimination reactions. Okay, all right. We're going to take a very similar reactant here. I'm going to add just one extra carbon, and that's going to complicate things a little bit. All right, I'm going to tell you that we have another elimination reaction here. Whoops. Okay, but I'm going to tell you things are a little bit more complicated now because we have not one, but two different alkene products that you can draw. All right, I want everybody to take a second. See if you can't give me those two alkene products that we would get from this reaction. Okay, so why do I have two possible products for this reaction here? Because I have two neighbors. Each one of those neighbors has a hydrogen that could potentially get lost in this elimination reaction. So I could have my double bond forming on one side, or I could have it forming on the other side. All right, so we have these two distinct products here. One with that double bond all the way on that terminal carbon, and one on the other side. All right, so again, because I have these two different neighbors, I'll color them. One's red and one's blue, I would get one product if the blue carbon lost its hydrogen. I would get a different product if the red carbon lost its hydrogen. All right, I got these two neighbors here, so I have two potential products. Cool. All right, so now we got two products. What is the major product? Okay, so for this, we got to learn a little bit more about alkenes here. Turns out that one of these are indeed the major product because one of these alkenes is more stable than the other. Okay, so what we have to do now is we're going to have to learn how to classify our alkenes. And this is a very similar process to what we've learned how to do for classifying carbons and classifying alkyl halides. Same sort of idea. Classification of alkenes. This is what we call our degree of substitution. All right, and just like before, we were counting carbon neighbors to figure out if it was a primary carbon or a secondary carbon. We're going to play the same game. We're going to count number of carbon neighbors. But since it's an alkene, we got two carbons, one on either side, right? So we're going to count the number of carbon neighbors on both sides of our double bond. All right, so what do I mean by that? Let's take an alkene here. But I'm going to stick this double bond on the very end. So what we're going to do is we're going to look on either side of our double bond, and we're going to count how many carbon neighbors there are, just to those blue carbons there. So in this case, I would only have one carbon neighbor. So this is what we would call a mono-substituted alkene. And we would use that little 1 degree symbol, similar like we do for a primary carbon, right? There's only one neighbor to that double bond, so that is a mono-substituted alkene. What if I pick up that double bond and move it to the middle here? Again, I'm going to look on either side of that double bond and count the total number of carbon neighbors. All right, so I got one here and one here, so this would be what we call a di-substituted. Or that 2 degree symbol. All right, I'm going to put down two more examples. I want you all to tell me the degree of substitution for each of these alkenes. Always playing musical chairs up there, huh? Okay. How many carbon neighbors do my two double bonded carbons have here? 1, 2, 3. So this would be a tri-substituted. Okay, and I'm only counting direct neighbors, right? It doesn't matter how many carbons we have coming off. That's still just a tri-substituted alkene. I'm only counting my immediate neighbors here. Or, yeah, we use that 3-degree symbol. Cool. So how many carbon neighbors do my double bonded carbons have in this last example? 4. So this would be a tetra-substituted. Okay? So just like we have our classification of carbons in our alkanes, we can also classify our alkenes depending on how many carbon neighbors are specifically about those carbons on both sides of the double bond. All right, so this is important because it turns out that there's a direct correlation between the stability of an alkene and its classification. Our least stable alkenes are those mono-substituted, and the most stable alkenes are those tetra-substituted, and it increases based on that degree of substitution. All right, so it turns out that the more carbon-carbon neighbors a double bonded carbon has, the happier it is, the more stable that compound is. All right? So we said that we were going to get we got these two products, and we said, well, what's our major product? Well, because of thermodynamics, our major product is going to be the one that is most stable. And as we just talked about, there's this direct relationship between the degree of substitution and the stability. So by most stable, that's really code for the most substituted. All right, so I want you to take these two products here and classify them according to their degree of substitution. Are you looking at a mono, di, tri, or tetra-substituted alkene? All right, that first product on the left there, that blue carbon, what's my degree of substitution? Just 1, right? Mono-substituted, absolutely. It's just got that one carbon neighbor attached to that blue carbon. Boom. And over here, this red product, what is that degree of substitution? 3, absolutely, yeah. 1, 2, 3 carbon neighbors. Again, I'm only counting what's immediately attached to those double bonded carbons. But absolutely. So then based on this, what's going to be my major product of this reaction? The red or the blue? Left or right? Red. Right? So we can say this is our major product. Okay? Let's do one more for practice before we move on here. right, again, I'm going to tell you that there are two products. I want you to draw those two products and tell me which one of those two products would be the major product of this reaction. Okay, so again, I have these two products because I have these two neighbors, one on either side. So if the blue carbon loses its hydrogen, I would get this product. And if the red carbon loses its hydrogen, I'll get my other product. Cool, so we have these two distinct alkene products here, and we want to know which one of these is our major product. What do we think, the one on the left or the one on the right? One on the left, right? Because this is a tri-substituted alkene. It's got these 1, 2, 3 next door neighbors to that double bond. And this one is just a mono-substituted alkene. It's only got one. Okay? Cool. All right, so let's just summarize real quick. Elimination, major products. All right, so our major product is always going to be the one that is most stable. That's what thermodynamics tells us, is that our equilibrium is going to favor the one with the lowest free energy. All right, and we said that that has first to do with our degree of substitution, right? So the more substituted alkene. But I'm gonna leave some room here because we got one more thing to consider here. All right, let's look at one more example. All right, again, we're going to take an alkyl halide. Again, we're going to do an elimination reaction. Okay, but for this one, I'm going to tell you that there are actually 3 distinct alkene products that you can draw. 2 of them should be pretty obvious based on what we discussed before. The other one, I want you to see if you can't figure out based on what we discussed. I'll give you a hint, that cis-trans stereochemistry that we talked about with our alkenes. Okay, so everybody take a second. See if you can't think of what those 3 products would be for this reaction. right, so we got two of them that were hopefully pretty easy, right? When I make my double bond on the left, I get one product. When I make it on the right, I get a different product, right? Check, check. Okay, so how do I get this third product here? Well, what's important to remember about our molecules, even though we draw them as these flat structures, as these 2D projections, they are not just sitting there standing still when they're at any temperature other than absolute zero. They're constantly moving around. And specifically, they're rotating about all of those single bonds, right? So this single bond right here is sitting there spinning around and around and around, which means that I could draw this exact same molecule like this. And now if I pick that red carbon and I form my alkene product, I'm going to have that same double bond between that red carbon, but now I'm not going to be in that trans stereochemistry conformation. I'm going to be in this cis stereochemistry conformation. And remember, these are two distinct molecules. Right? Double bonds cannot rotate. So if my double bond forms with these two methyl groups on the same side, they're stuck there on the same side. Likewise, if it forms with those methyl groups on opposite sides, they're frozen there on opposite sides. Right? So I have these three distinct products, one where it formed on one side, but then two where it formed on the other side. And again, remember we had fancy terminology. When these two groups are on opposite sides, we call that our trans stereoisomer, and when they're on the same side, that's our cis stereoisomer. Okay, so now again, we can ask that same question here. What is our major product? All right, well, right off the bat, one of these is out of the running, right? Which one of these am I going to nix immediately? 1, 2, or 3? 1, right? This is already the less substituted out of the two, so this is my minor product here, okay? But between our cis and our trans isomer, which one of these is going to be our major product, okay? So we're going to add to our stability of alkenes conversation here. All right, we'll call this stability of our alkene stereoisomers. All right, and let's just take our two examples, the trans 2-butene and the cis-2-butene. Turns out that one of these molecules is a little less stable than the other one. All right? And this just goes to this very simple principle in chemistry called sterics or steric hindrance. Which is kind of just a fancy way of saying atoms don't really want to be next to each other. Atoms want to be as far away from one another in space as possible. When they're crammed next to each other, it just necessarily raises the energy of those molecules. So by steric hindrance, we mean atoms want to be as far away in space as possible. All right, so if I look here at these two stereoisomers, my cis and my trans stereoisomer, which one is going to be the more stable of the two? The trans isomer, where those two groups are on opposite sides of the double bond, or the cis isomer, where they're crammed together on the same side of the double bond? our trans isomer, right? So this one's going to be more stable. This one's going to be less stable. And again, that's simply because these two methyl groups right here have more room. Our two methyl groups are further apart. All right, and the bulkier the group, the more carbons, the less it wants to be next to anything else, right? So we're always going to put the two big groups on opposite sides of our double bond. That's going to be the most stable alkene. All right, so then let's just finish this off here. What would be my major product here? 1, 2, or 3? 2. So this is my major product in the middle. This is another minor product over here. Okay, so our elimination reactions here. The first consideration is the substitution of that alkene. Okay, that's going to be your first, like, I'm going to figure out minor products based on substitution. But our second one here is we want those big groups of atoms on opposite sides of the double bond. All right, and now our third rule, which is the hardest out of all of them. No, I'm kidding, actually, we're done there. So that's like kind of it for this particular chapter, all right? But let's just kind of take a minute and summarize, because this last part is sort of subtly difficult here, finding all of our products and figuring out which one is the major one. So let's just do a few more examples of these elimination reactions. right, so for this first one, we're going to look. We got 2 carbons on either side. So I'll get one product if it forms with that red carbon. Okay. I'll get a different product if my double bond forms with that blue carbon. Oops. All right, and do I have any other products? I got one more here, all right? And that is if I swapped this hydrogen and this methyl group here. Still forming between that blue carbon but now instead of having that trans conformation, I have my cis conformation here. Okay? Cool. So, which one of these is going to be definitely a minor product? The first one here, the less substituted, right? So our rule 1, degree of substitution, the most important thing to consider. This is a mono-substituted alkene compared to the other 2, which are both di-substituted alkenes. Right? But out of my other 2 products, which one is going to be the most stable? When these 2 are pointed on opposite sides of the double bond or on the same side of the double bond? Opposite sides, right? So this would be my major product. This is another minor product. All right, so let me make some space real quick. Okay, how do I know that this one, for example, had these 2, whereas this one didn't, right? How am I supposed to know whether there's another stereoisomer that I can draw here, all right? The important thing that makes this one not have a second product, I don't have to flip anything here, is I have the exact same bonds on one side of that double bond. Both of these are hydrogens. So if I flipped this over here, it's just going to be next to another hydrogen, right? So if I ever have either of these carbons that have 2 identical groups, that's the only alkene that you can draw for that particular molecule. If I look over here though, this is a methyl group and a hydrogen. Those aren't the same. This is that 3 carbon, what's called an isopropyl group. Who cares? And a hydrogen. Not the same, right? So if I swap these, I'm going to have a different product. All right? So let's just make a note here.
Can you re-explain that?
Yeah, we're going to summarize here. All right? So how do I know to draw another product? I don't know why I'm putting it there. Okay, my carbon on either side cannot have 2 identical groups. If it has two identical groups, that's the only possible alkene that you can draw. If you flop things around, you're just going to draw the same molecule again. So how do I know that I have to draw another product? The carbons cannot have identical groups on either side. Or rather, the carbons on either side cannot have two identical groups. So again, this one up here, I did not draw a second product because this carbon had two identical groups, two hydrogens. This one I did because neither one of these carbons had two identical groups on it. Let's just go back to one of the examples that we did at the very beginning. Okay, this was an example that we did before we talked about cis-trans stereochemistry at all, right? And I was able to do this example without having to worry about that. Why? Because neither one of these has any sort of stereochemistry, meaning this has these two methyl groups, two identical groups. If I swap them, I'm not going to get a different product, right? Over here, this one has two identical groups, these two hydrogens. If I swap them, I'm not going to get a different product, right? So if it has two identical groups, that would not lead to a third product there. That's all we can draw. Okay, so then I want you all to take a second and apply that same logic to your products here. I think everybody probably, hopefully, was able to get the first two, where we take our double bond and put it on either side. This one's over here. Okay, if we look at this one, I'm going to look at this carbon first. And I'm going to say, are the two groups on this side the same? No, one of them's a methyl group, one of them's a hydrogen. Those are different. If I look on the other side, are these two the same? No, one of them's a methyl group, one of them's a hydrogen. So if I swap these two here, I'm going to have a different product. And actually, you could choose either side of your double bond to swap. It's kind of easier to pick the side that's smaller. But you'd get the same product either way. So now what I'm going to do is I'm going to take that methyl group, and instead of pointing it down, I'm going to point it up. And those are two distinct products. All right, let's do this one here. Are both groups on this side of the double bond the same? No, one of them's an ethyl group, one of them's a hydrogen. What about this side of the double bond? No, one of them's an ethyl group, one of them's a hydrogen. All right, so then draw me, it's the other product here. When you flip two of these groups, you're going to swap this hydrogen for that two carbon group there to give me my other alkene product. All right, so I'm going to start the same, but now when I get to the other side of my double bond, instead of putting my carbon down here, I'm going to put my hydrogen down here. And instead of putting my hydrogen pointed up, I'm going to put my carbon pointed up.
So in that case, would you have the control to make it either a cis or trans?
You're going to get a mixture of all of them, right? But the question is, which one's the major product?
Oh, okay.
Okay, so first of all, we have two different alkenes. One of them is 2 hexene. The other one is 3 hexene. So the position of my double bond is different from the left to the right. But then I also have for each of them a cis and a trans stereoisomer. Kind of bother me floating out there. Cool. All right, so because we had that, we looked on either side, and for both of our products, neither of those carbons had the same groups. We actually have 4 distinct products here. All right, we said that first was degree of substitution. What is the degree of substitution of all of these products, actually? Secondary, yep. Or not secondary, di substituted, but yes, 2. Okay. So then now we got to go to rule 2 here, which is just that those big groups like to be on opposite sides. So which 2 of these are definitely not my major product? These 2 here, and this one especially is bad because those are even bigger groups next to each other on over here. But nonetheless, those are 2 my minor products. All right, and my top 2, they have the same degree of substitution. They both have big groups pointed on opposite sides. So we're going to get a 50-50 mixture of both of these here. They would be our major product for this reaction. All right, they tie both rule 1 and rule 2, so they're both going to be our major products. Cool. All right, practice is going to make perfect here. Again, just to be clear and start kind of simple, when I'm trying to draw my stereoisomer, what did I do? I swapped those 2 groups, right? Swap to draw my other stereoisomer. Okay, and I mean, just to be clear, cool. Break. Yeah.
So for this one, you said that this was the major, or the major product was this one, and that was the minor product?
Correct, yeah. Because
So-
this one, this carbon, these 2 groups are on the same side of that double bond.
Okay, I thought, see, this one was going downward and that was going upwards.
But look at these 2 groups right here. They're right next to each other.
Okay.
Whereas over here, this one's pointed away from that little fork right there.
I see.
Here it's pointed on the same side as that fork. Here it's pointed away from the fork.
Got it. Thank you.
Yep.
That's a lot.
Yeah, it's going to be a practice makes perfect for sure.